Hello and welcome. Today we're going to be discussing the problem swap to win. In this question, we're given two operations. The first operation allows us to swap two letters within a string. The second operation allows us to swap two letters between two strings, as long as those letters are at the same index. And in this question, we're going to be given a string t of length m, and then a list of n strings, all of length m as well. And our goal is to use at most 2 to the m operations in order to transform the first string in our list to be equal to the objective string t. And note, since it's saying at most 2 to the m operations, this is an upper bound. We can use fewer, but we don't have to, right? So this is not an optimization problem. We don't have to find the minimum number of operations necessary. So let's take a look at an example. If we had our objective string as USACO, and 4 different strings on our list, our objective would be to turn this very first string S0 into the string USACO. And what I've done to make this a little bit easier for you guys to see is I've starred out every letter that's not relevant, but these stars would be other junk characters like M's and O's and Z's and J's, right? So I've started out so that we can just see exactly where the letters are located. And we're going to be trying to swap these letters around so that eventually the first string spells USACO. And what you can see is some of the letters might start in the correct position. For example, this A is already in the right spot. And what we're going to want to do as we're working through this by hand is we're just going to want to go letter by letter and move the correct letter into position. So we're going to want to move the U into position, then the S into the correct position. A we can skip because it's already right. Then we'll fix the C, and then we'll fix the O. So starting off with the U here, we can see that the U is in the correct index, but it's in the wrong string. So what we're going to do is we're going to apply the operation type 2 in order to swap the first letter in S0 with the first letter in S1. And when we do that, you can see that the U transforms from the first from S1 to S0, and we now have U in the correct spot, and we only used one operation to do that. Fixing the S is going to be a little bit harder because it's both in the wrong string and it's in the wrong position. So the very first thing we're going to do is we are going to swap its location in the string that it's already in so that it's in the correct position. And then we are going to apply the second operation in order to correct the string it's located in. So we're going to take it from S2 and we're going to swap it into S0. So in total, we used 2 operations to fix the second character. And in fact, we can always use 2 operations to fix a character. That's why it's giving us at most 2 M operations here. We have M characters that we need to fix. We can fix any character using 2 operations. So in total, we get 2 M operations, which is really good news for us because this means that we can probably use brute force to solve this problem. So far we've corrected U, S, and A, and now we just need to fix the C and the O. Just like the S, the C is both in the wrong string and the wrong position. So we are going to swap it within the string that it's currently located so that it's in the correct position. And now, once we've done that, we are going to swap it into the correct string. So we're going to take it from S3 and move it into S0, again, using 2 operations to do that. And the O is easy. The O is in the wrong string, but it's already in the right spot. So we're again going to apply operation 2 to swap it into the right spot. And you can see that S0 is now equal to the objective string. And in total, we used 6 operations, which is less than the maximum of 10 operations that we were allowed to use. So in this problem, since it's not an optimization problem, that means that brute force is going to be a very realistic solution here, right? We can brute force search over the entire list of strings to find the character that we need, and then we can do 2 operations to swap it into the correct place. So we're going to loop over the objective string t. We're going to ask, what is the next character we need? We're going to loop over all of our n strings to search for that character. We're going to look for a copy of it. So for example, if the current letter that we're looking for is S, I'm going to loop over all of the strings until I find a copy of S. And then once I find that copy of S, then I'm going to use 2 operations to move it into the correct position. So I'm going to use one operation to move it into the correct index and a second operation to move it into the correct string. However, one thing we want to be a little bit careful about if the letters in the objective string aren't unique, we don't want to accidentally use letters that we've already sort of fixed the position of in order to sort of fix future letters, right? So let's say if we had USA and then we wanted to find another S later in the string, we probably shouldn't use the S that we've already placed in the first part of S0 in order to move it over here, because now we might end up with sort of some random junk in the first part of our string. So what this tells us is that when we're searching for a copy of the letter, we should start by searching the strings after S0. So we should always sort of like grab the strings from the letters from S0 in the worst case, but we should begin by searching all the other strings because we don't care what those strings are in the end. And then if we are searching S of 0 for the next copy of the letter, we should start at the end of S0 and work our way backwards. So we want to be careful. We don't want to move any letters that we've already put into the correct position. That's one way we can sort of accidentally end up using more than 2M operations. So if we've already put a letter in the correct position, we never want to move that letter again. And one way to fix this is we can just loop over the strings from largest to smallest and loop over them in reverse. There's like a million different ways you can solve this problem, but the key idea is just never move a letter once you've already put it in the right spot. However, if you have looked at the problem already, you will know that there is an additional problem with this brute force strategy. And the problem here is that N and M are both size 1000, and the runtime of this algorithm is going to be N times M squared. So at the moment, we have at best a partial credit solution. And where does this runtime come from? Well, the loop over T, this is a loop over M characters. And then if we have to search the entire grid of characters to find the character we're searching for, this loop is going to be a loop over N times M characters. So we have a loop over N times M characters inside a loop over M characters for a total runtime of N times M squared. So this is going to be problematic for us in the future. However, what I would encourage you to do on this problem is, unless you have a better idea, begin by coding the partial credit solution. And we're going to see that the partial credit solution in this problem is very quickly going to turn into a full credit solution. Because the idea is that when we write out the partial credit solution, we're going to end up with 3 nested loops. And we just need to eliminate one of those loops. So once we have the partial credit solution, we can take a look at our code and say, which of these loops can I eliminate in order to make my program faster? So for now, we're going to do something a little bit different than what we usually do in these videos. We're going to talk about the partial credit solution first, which is just brute force. And then we're going to analyze that brute force algorithm to see how can I make this faster. So what I've got going on the left side of the screen here is simply the beginning of the program where I'm looping over the T test cases, and then I'm reading in the input. So I'm reading in N, which is the number of strings, M, which is the length of the strings, T, which is the objective string, and then S is going to be my list of strings. So this is a list of N strings, each string being length M. And we want to start off by trying to write exactly this brute force algorithm here. So we're going to be looping over the string T, and our objective is to find a copy of TK. So this is the current letter in the objective string that I'm looking for, and I want to move it to position S0K. So this is just going to the first string in my list and updating it to be in position K. I'm going to have a variable called found that is going to allow me to break out of my nested loop here as soon as I find the first copy of TK. And going back to this cautionary note from earlier, again, I'm going to be looping over the strings backwards. So I start searching the strings that are not S0 first, so that I don't accidentally rearrange any characters that I've already fixed in S0. So if there's a copy to be used in some of these later strings, I'm going to prefer those copies because, again, I don't have to be efficient in this algorithm in terms of the number of operations I use. I can be a little bit wasteful and grab characters that are going to require 2 operations instead of grabbing characters that are going to, say, require 1 operation. So I'm going to loop over the strings backwards. And for the current string X, I want to answer the question, does TK exist in the current string. And in order to know, does a copy of tk exist in the current string, I'm again going to have to loop over all characters in the current string. And so here you can see that nested loop over the grid of strings. So I've got an n by m grid here, and I'm looping over all positions in that grid, and I'm checking, did I find a copy of tk? So is the x string at position p equal to the character I'm looking for? If I have found a match, then all I need to do is apply the two operations necessary to move t of k into position s0k. So the first operation I'm going to do is apply operation 1 to move the copy of tk inside the string s of x. So that's what we are doing, for example, right here when we are moving s from position 4 to position 2. We are applying operation 1 so that later I can apply operation 2 to move it into the correct slot within S0. So the second step is I'm going to apply operation 2 to take that very same character and move it into the correct position of S0. So we're simulating in the code exactly what was done right here in the example. Swap the position of S to the correct index in S2, and then swap S into the correct index in S0. And since I'm allowed 2 to the m operations, I'm just always going to do these two operations. Again, there might be a more efficient way of doing it where I need maybe one operation or maybe even 0 operations to do this. But I don't need to think about any of that casework because I can always just apply 2 operations, even if the operations just end up leaving the character exactly where it was before. So I'm going to be as lazy with my code here as humanly possible. And then finally, since I found the copy of tk that I was looking for, I'm going to update found to be true, break out of the loop, and then break out of the second layer of the loop, and then print out the output when I'm done. Now that we have our partial credit solution, we can think about the question, how do I make it faster? Because the only thing I don't like about this code is these 3 nested loops. And I have to remove one of them in order to make this fast enough to pass all the test cases. I can't really eliminate this loop because I have to loop over every single character in the objective string in order to correct that character. So I really can't eliminate the first loop. So the choice is going to be between one of these 2 loops. Either I need to eliminate the loop over all strings, or I'm going to need to eliminate the loop over all of the positions within the strings. And anytime I think about the idea of eliminating loops in the context of bronze USACO, I always want to think about the idea of pre-computation, right? What can I pre-compute in order to find the information I am searching for faster, right? So I'm searching for which string currently contains the letter TK inside it. So maybe there is some way I can pre-compute which strings contain each letter so that I don't have to do as much looping in order to find the location of each letter. And in particular, I can pre-compute a list of strings that contain each letter. So for the letter A, I could write out a list of every single string that contains the letter A. For B, I could write out a list of every single string that contains the letter B. For C, I could write out a list of every single string that contains the letter C, and so on. And this would allow me to, instead of having to search over all the strings, I could instantly grab a string that contains the current letter. Because I have a list, let's say the current letter is C. I could go to the position for C in my list and say, give me the index of a string that contains the letter C, and I can eliminate this loop by just instantly popping off one of the strings that contains the letter C. There are other ideas as well. You could maybe solve this with frequency arrays, right? Keeping a count of how many copies of each letter does each string have, and that might allow you to check, does this string have a letter faster than looping over all of the positions? But I think this idea of pre-computing where all of the letters are stored is a very nice idea here. So what we're going to do is we're going to pre-compute this list, and then we're going to see how I can use that list in order to eliminate this loop. So we are going to create this data structure called letters. So this is an array of empty arrays, and it stores which strings contain each letter, and I'm going to index it via the ASCII table. So 200 is just an arbitrarily large value here that's sufficient to cover the ASCII values of the letters in the alphabet. So the ASCII value of A, for example, is 97, and the ASCII value of Z is something like 122. So it's just a value large enough so that every letter can be indexed by its ASCII value. And then what I'm going to do in my pre-computation step is I'm going to loop over every single letter in my grid, and I'm going to go to the index corresponding to that letter, and I'm going to add I to that array. And this is saying that the string stored in position I contains a copy of the current letter. So if I want to know which letter or which strings contain this letter, so ORD here is just the Python way of calculating an ASCII value, but this is just a particular letter. If I want to know which string contains this letter, I can just access this very same slot in letters. So for example, if I wanted to know which strings contain the letter C, I would just go to letters at the order of C, and this would return to me a list of every single string that contains the letter C. So for example, if the letters array returned this, that would say that string 0 contains C, string 1 contains C, string 4 contains C, and string 5 contains C. So instead of using this loop to check for where T of K is located, I'm going to be able to collapse this loop into just a single check of the letters array. So I'm going to do X is equal to letters of ORD of TK. Remember, TK is the letter that I am searching for. And I'm just going to pop out one element from that list. And now I can sort of remove one indent in my code because I've eliminated that loop. And now I don't need the found variable anymore either, because I'm no longer going to be using a nested loop here. I can just break out of the single loop immediately. So I don't have to loop over all strings. I can instantly just pop out the index of one of the strings that contains TK. At this point, the code passes all test cases. However, there's technically a small bug here. While the string at position X did lose a character, in particular, it lost the character stored at S of X P. It did gain a new character, and it gained the character that used to be stored at position 0K, right? So when we swap, let's say, this S into string 0, the letter that used to be in the string 0 is now in string 2. So if we want to be very particular about our solution, we should add one extra line of code here, which adds in the new character that the string in position X received from the string in position 0 when we did this swap. So again, the code passes all test cases if you don't have this line, but you can come up with test cases where the code fails unless you include this line. So we do want to make sure that our code is actually correct, even if their test cases don't include that bug. And what we can see here is that the full credit solution ends up being shockingly similar to the partial credit solution, with the only difference being we have to do a little bit of pre-computation to eliminate that loop over X. So now step 1 has just become instantly find a string SK that contains TK. And the reason why we can do that instantly is because we pre-computed the location of all of those things. And just to show you a quick comparison here, on the left side of the screen, I have the partial credit solution we had originally come up with. And on the right-hand side of the screen, we have the full credit solution that we ended with. And what I've done is I've lined up the codes so you can see the parts that remain the same, right? So these two lines remain the same. This block of code is identical to this block of code. And what you'll be able to see if you investigate this is that pretty much the only change that we had to make between the two programs is this singular loop. right? We had to eliminate this loop, but the rest of it stayed pretty much the same, right? And in order to eliminate that loop, we had to do pre-computation, but eliminating this loop was the key thing. So oftentimes I have students who don't want to code the partial credit solution because they want that full credit score right away. But coding the partial credit solution can be a very good path to actually discovering the full credit solution, right? So if you are stuck on a problem and you don't instantly see what is the full credit solution, always code the partial credit solution if you don't have anything better to be doing with your time, because you can oftentimes turn those partial credit solutions into full credit solutions. You can see the two codes here are almost identical. And that is the key message behind this question. If you're stuck on a problem, code the partial credit solution. It can turn into full credit solution ideas. On that note, thank you so much for watching the video. Have a wonderful day, and bye-bye.